In this video, we will continue to summarize the preparation and reactions of various carboxylic acid derivatives. Let's think about the preparation and reactions of esters. So if we start out with a carboxylic acid, this can be treated with an alcohol in the presence of H+, and this is a Fischer esterification to give an ester. This can also be done by an SN2 type of reaction where an acid is first treated with sodium hydroxide to pull off this proton, and then this acts as the nucleophile treated with an alkyl halide to give an ester. Alternatively, an acid chloride or acid bromide can be treated with an alcohol. It will undergo nucleophilic acyl substitution to give an ester. This can also be done with an anhydride. So there are other ways that esters can be made. These are some of the common ways. So what about reactions? Keep in mind, esters cannot be converted into acid halides or anhydrides by nucleophilic acyl substitution. They could react with an amine to give an amide, but that's not really common. They can be hydrolyzed under acidic conditions or basic conditions to give a carboxylic acid. They can be reduced using lithium aluminum hydride followed by water, and they would be reduced to a primary alcohol and your other alcohol as well. They can be reduced using diisobutyl aluminum hydride, and this is usually carried out at -78 degrees, and this one will stop at the aldehyde and does not get reduced all the way down to the alcohol. So you will get an alcohol corresponding to this side, but this is reduced to an aldehyde and then it stops there. And finally, one other reaction we've seen is treatment with a Grignard reagent. So step 1, step 2, H3O+, and this will give us an alcohol resulting from the addition of 2 equivalents of Grignard. So the first equivalent does nucleophilic acyl substitution where this is kicked out, giving us a ketone, and then a second equivalent will add to the ketone, giving us this alcohol. So these are some of the most common ways of making esters and some of the important reactions of esters as well. Another important thing about esters is that if you have a molecule with a carboxylic acid and an alcohol in the same molecule, and this is exposed to acidic conditions, it can undergo an intramolecular esterification to give a cyclic ester. Now, a cyclic ester is called a lactone. So an intramolecular esterification reaction is called a lactonization. Typically, these are characterized by the size, and so if we focus on the carbonyl carbon, the next position is alpha and then beta, gamma, delta. So this is a delta lactone. If a hydroxy acid can form a 5 or 6 membered ring, then the lactonization will be spontaneous with just a little bit of acid. If you're trying to make a smaller ring, 3, 4, or a bigger ring, 7, 8, or bigger, then it's not as easy. Now, there are many important natural products that have very large lactones. This is erythromycin A, and we can see we have an ester, so this is a ring, so this is a lactone. Now, because many important natural products have really large lactones, these are called macrolactones. There have been special methods developed to make these macrolactones, and so there are methods for macrolactonization. For a long time, there were a number of Japanese groups that developed methods that could be used to make lactones in natural products. And so there is the Mitsunobu macrolactonization, Yamaguchi macrolactonization, Mukiyama macrolactonization, and this is just a small sample. So down here, we have an example. So here is a carboxylic acid and here is an alcohol, and these are the two that need to be made into an ester. But rather than just trying to close this up, Corey and co-workers used a special macrolactonization method where the acid was converted to this special thioester, and then this can undergo reaction to form this macrolactone. Now this is converted in several additional steps to give this compound, erythronolide B, which has been used as an antibiotic for decades. Amides can be prepared by nucleophilic acyl substitution of acid halides, anhydrides, or esters. So any of these with reaction of an amine can be converted to the corresponding amide. Alternatively, a nitrile can be partially hydrolyzed to an amide. And one other approach would be combination of a carboxylic acid with an amine to give the amide. This can be done using really high temperatures, which makes it not very general, or more likely it can be done with particular coupling agents. Now, as we think of reactions of amides, these can be hydrolyzed either under acidic conditions or under basic conditions, and that will give carboxylic acids. Amides can also undergo dehydration using phosphorus pentoxide or phosphorus oxychloride to give nitriles. And this would only work on primary amides where both R primes are hydrogens. Or amides can be reduced using lithium aluminum hydride followed by water to give an amine. So using lithium aluminum hydride, remember this is a source of hydride, so this can share its electrons with the carbonyl carbon, push these electrons up onto the oxygen, giving us as an intermediate something that looks like this, where this oxygen is going to be complexed with aluminum trihydride. Next, the nitrogen can share its electrons here, pushing away oxygen, which is going to be complexed with the aluminum, giving an iminium ion that looks like this. And then finally, reaction of another equivalent of hydride. This can add to the carbon, push these electrons onto the nitrogen, giving us our amine. So the R group, the carbon, the nitrogen, and these R prime groups were all originally present on the amide, and these hydrogens are both from the lithium aluminum hydride. So just a little bit more to consider in terms of amides. Just a moment ago, we saw that a cyclic ester is called a lactone. Well, we can also have a cyclic amide, and this is called a lactam. Once again, focusing on this carbon, alpha, beta, gamma, delta. So this is a delta lactam, for example. Here is an example of a beta lactam antibiotic. So penicillins, for example. This is the cyclic amide, so this is the lactam, and this is the alpha position beta. Beta is connected to the nitrogen, so this is a beta lactam. Notice we also have an amide over here. So like most amides, this is not very reactive. Beta lactam, it's not reactive because it's an amide, but this is highly strained. A four-membered ring is going to be highly strained. So a beta lactam is reactive. So this is important because many of these beta lactam antibiotics can react with an enzyme that is responsible for building cell walls, and this can react here, push up these electrons come back down, open up the ring, and so it will give you something that looks like this. And up here we still have our regular amide. But notice this enzyme is now covalently bonded to this molecule. And so the active site of the enzyme is no longer active. So the enzyme is effectively dead, can't build the cell wall, which means the bacteria can be killed. So with a number of beta-lactam antibiotics, these groups can be varied, but more commonly the R group can be varied, and that's going to affect properties such as adsorption or distribution, how it's metabolized, how it's excreted. So a lot of antibiotics with this general structure have been developed. Now, as we're thinking about penicillins and other beta-lactam antibiotics, we all know that Alexander Fleming was given credit for discovering penicillin as a very useful antibiotic. It's a very interesting story because his discovery was somewhat accidental. He kept a very messy lab, went on vacation, came back, and found that something was killing the bacteria that were left on the plates that he didn't clean off. And so, yes, he discovered the particular compounds, but it was Flory and Chain from Oxford, as well as Heatley from the USDA, who developed fermentation methods to be able to make larger quantities of penicillin so that they could be used as antibiotics. So this was happening during World War II, where antibiotics were critical. And until there were methods to be able to make penicillins in very large quantities, the antibiotics were so critical that they were actually isolated from urine to be able to reuse the compounds. Also of note is Dorothy Crowfoot Hodgkin, who solved the X-ray crystal structure for penicillin, and determining that structure was also very important to be able to make large quantities of penicillins, and also to be able to make variations of the penicillins that could be effective against different types of bacteria. Nitriles can be prepared by nucleophilic substitution of an alkyl halide. Nitriles can be prepared by nucleophilic substitution of an alkyl halide. So treatment with cyanide, this can do SN2 substitution to give a nitrile. Another approach would be dehydration of a primary amide, where this can be treated with phosphorus. This can be treated with phosphorus pentoxide or phosphorus oxychloride to give a nitrile. To give a nitrile with the loss of water. And another approach would be nucleophilic addition to an aldehyde, where we might use cyanide followed by dilute acid to give a cyanohydrin. So here we have a cyanohydrin. For reactions of nitriles, partial hydrolysis using mild aqueous acid would give an amide, whereas more complete hydrolysis using more forcing conditions would give the carboxylic acid. So whether we have mild conditions or stronger conditions, that would determine whether the hydrolysis stops at the amide or continues to form the carboxylic acid. Nitriles can also be reduced using lithium aluminum hydride followed by water, and this will give a primary amine. Or nitriles can react with a Grignard reagent followed by aqueous acid workup, resulting in the formation of a ketone. So the R and the carbon, so the R group and the nitrile carbon are maintained as the R group and the carbonyl carbon, and then R prime comes from the Grignard reagent. Let's take a look at the mechanism of nitrile hydrolysis in case you're interested. If we have a nitrile and we react it with H3O+, this would have to be pretty concentrated. The nitrogen can grab a proton, and that will give us a protonated nitrile, where this nitrogen has a positive formal charge. That is going to make the nitrile carbon more electrophilic. So water can now add to this carbon, pushing these electrons onto the nitrogen. So this is a double bond, lone pair, hydrogen. The carbon is connected to oxygen, which is still connected to the two hydrogens. It has one lone pair and a positive formal charge. There will be another proton transfer. Water can grab off this proton, giving an imine. Actually, this would be the imine version of an enol. This can get protonated again. And keep in mind, if the oxygen grabs a proton, we're just going backwards, and so that's going to happen. This is an equilibrium. But if the nitrogen grabs a proton, then we get something else. So let's picture that, and that is going to give us NHH plus H. Now, oxygen can share electrons with the carbon, putting electrons onto the nitrogen. And another proton transfer will give an amide. Hydrolysis of a nitrile leads to an amide. Depending on the specific reaction conditions, hydrolysis of a nitrile could stop here at the amide, or it can continue forward to the carboxylic acid. So we're still looking at the hydrolysis of a nitrile. And on the last slide, we saw that it goes to form an amide. So from here, we're still under acidic conditions. So the oxygen can grab a proton and water can act as a nucleophile, pushing these electrons up onto the oxygen. Giving this intermediate. Next, we would have a couple of proton transfers. So water can grab off one of these protons, and H3O plus can give up a proton to the nitrogen, and that would give this intermediate. These electrons can restore the carbonyl, kicking out, in this case, NH3. And then finally, one more proton transfer gives the carboxylic acid. Now, this was just in case you're interested. Nitriles can be reduced with lithium aluminum hydride to give an amine. So 2 hydrogens are added to the carbon of the nitrile, and 2 hydrogens are added to the nitrogen of the nitrile. These 2 hydrogens both come from the lithium aluminum hydride reagent, and these 2 hydrogens both come from water. You are not responsible for the mechanism, but I'm just going to go over this in case you are curious. So keep in mind, lithium aluminum hydride is a source of hydride ion. And so this can donate its electrons to the nitrile carbon, pushing these electrons onto the nitrogen. So now we have 2 lone pairs on the nitrogen, and it has a negative formal charge. And this is, the carbon is now connected to a hydrogen, which came from the lithium aluminum hydride. Now another equivalent of hydride can add, and this is one that probably doesn't seem very believable, and it's because I am skipping some details, but that would give us a single bond to nitrogen with 3 lone pairs and a charge of -2, and a hydrogen connected to the carbon. So the detail that I'm skipping is that because we started out with lithium aluminum hydride, when we donate a hydride, we now have aluminum trihydride, which is going to have a positive charge. So in these intermediates, this nitrogen is going to be complexed with some aluminum species, which makes this more reasonable. Okay, and then when this is worked up with water, this can grab a proton and this can grab another proton, and that will bring us to H and H. So the nitrogen still has 1 lone pair. Again, notice this was our hydride and this was our hydride. So this is our hydride. So in the end, these two hydrogens came as hydrides. And then this and this came as protons from the water. So if you want to know how this works, then here is some information. Mainly what I want you to know is that nitriles can be reduced by lithium aluminum hydride to give an amine. The last reaction of nitriles that we're going to talk about is the reaction with Grignard reagents. Now, one thing I forgot to mention, when we think about a carbonyl compared to a nitrile, with aldehydes and ketones, we just talked about a whole bunch of nucleophilic additions, and so we had already talked about Grignards and organolithium reagents, but then we also talked about adding an amine or an alcohol or cyanide. So all of these milder nucleophiles can add to an aldehyde or a ketone. But those milder nucleophiles cannot add to a nitrile. So this carbon is not nearly as electrophilic as this carbon. The one exception, though, is if we have a really good nucleophile, such as H-, which we just saw on the previous slide, or R-, which is what we have with a Grignard. Grignard reagents can add to nitriles. The product, though, might look a little surprising because what you end up with is a ketone. So notice this piece becomes this piece, and this ends up here. All right, so what's happening? Just as you would expect, the Grignard is a source of a nucleophilic carbon, so this is going to share electrons with the carbon, pushing these electrons onto the nitrogen. Let's see if I can stick with color coding. So this is the CH3 from the Grignard reagent. Next, on aqueous acid workup, the nitrogen, first of all, can grab a proton, and we will get this intermediate. Notice this is an imine. And keep in mind, we saw a couple of chapters ago that if you had an aldehyde and you reacted it with an amine, that would give you an imine. Well, keep in mind, these reactions are reversible, so the aldehyde plus the amine gives you an imine plus water. Well, here we have lots of water and we have an imine, so this reaction is reversible. Sorry, I'm going to fix this here. Okay, so we've got more H3O+, so the nitrogen can grab another proton, and that will give CH3, C double bond N. So these hydrogens are coming from water, and this came from the Grignard. And now nitrogen has a positive formal charge. Water can add here, okay, pushing these electrons here. This gives H3C single bond N, H2 and a lone pair. And this is the CH3 that came from the Grignard, and this is from water. This can go through a couple of proton transfer steps. Remember, we have water, we have H3O+, so the nitrogen can grab a proton from here, water can grab a proton from here, and I need to write this really small. This will give us the CH3C NH3 plus connected to OH connected to CH3 that came from the Grignard. Next, one of these lone pairs can form a carbonyl, kicking out ammonia, And that is going to give us CH3C double bond OH plus and the CH3. And then finally, one more proton transfer step. This can grab off a proton, put these electrons back here, and we get a ketone. So the Grignard adds to the nitrile carbon, and after some proton transfers, it leads to an imine. And then the imine undergoes the reverse of nucleophilic addition of ammonia to an aldehyde or ketone, right? It goes through the reverse so that the isolated product is the ketone. In this case, ammonia, this would be kicked out here. That would just be bubbled off as a byproduct. So in general, I think it's helpful to be able to follow the electrons here, think about an acid-base step here, and then just recognize that this is the reverse of nucleophilic addition to an aldehyde or ketone to be able to predict the final product. So remember, what was the nitrile is now a carbonyl containing compound, and what was the Grignard is now connected to the new carbonyl carbon.